Hi everyone, welcome to our tutorial. Today we will continue from lesson 2 regarding the general frame input. First, we will look at the reinforcement cover and the top reinforcement axis step limit. What are the difference between this input? We have a look on this summary together. By default, RAPT will give you a number. However, user can define own preferred concrete cover. First, we will see that the top reinforcement cover, meaning the dimension to the top face of the top design reinforcement layer from outside top face of the concrete. For bottom reinforcement cover, the dimension to the bottom face of the bottom design reinforcement layer from the outside bottom face of the concrete. In this picture, we can see that the top reinforcement cover can be defined as C or CT. And then another top reinforcement axis step limit and bottom reinforcement axis step limit. This point is referred for the fire resistant design. The definition of concrete cover here meaning that it considered as the minimum depth from the top surface of the concrete to the center line of any reinforcing or precessing steel. For example, in this picture, we have the outer surface of the structure. This is the reinforcing or pre-stressing steel. From the center line to the outer surface of the concrete structure, represented by the letter A, the axis distance. So now we understand the difference between the two terms. In RAPT, we can tie the top reinforcement cover by 40 and top reinforcement axis step limit a little bit higher than the top concrete cover. When we tie, for example, we put 30 mm concrete cover top and bottom, this value will automatically resulting into the default setting in the design zone that we click here. We see that the top cover at left end 30 mm, top cover at right end 30 mm. If we change the concrete cover value from 30 to 40, we will understand that in the design zone, it's automatically changed according to what we input earlier. The user do not worry much about the input in this because when during the design, we can modify during the design zone or either in the defined reinforcement by user. So this now we understand the input between the reinforcement cover and top reinforcement axis step limit. Next, we will go to the span input. In this span input, the first thing that we need to look at is span. We have the LE, 1, 2, and RE. LE refers to left end. It means the left end of your structure here. 1 is span 1, meaning from here to here is span 1. 2, from here to here is span 2. RE means right end, refer to this location. And then we have the symbol span length. For left end, we put 0 because we have a pin support here. We don't have any extension of the structure beyond the grid line number 1. For span 1, we prefer 40,000 mm or equal to 4 meter. The second span is 5,000 mm or 5 meter. Next one is the slab depth. we prefer our slab that 200 mm for both span. After this, you will see the panel width left and panel width right. User can define the different panel width between each span. For here, this is the panel width left. We put 500 mm because our beam design will represent the 500 mm width. That's why we input here is panel width refer to the equal to beam width. The same here, panel width right, we also input 500 mm, which means equal to the beam width. Next, we will go to the column. By default, we see that the picture here display a pin support at grid line 1, 2, and 3. From point 0 to grid line 2 is 4000 mm, 4 meter. From 2 to 3 is 5000 mm, 5 meter. In here we have 9000 mm. The two span combined together is 9 meter. Here is the column 1. In the column 1 is the grid line 1, 2, and 3. But do not confuse between this column number and the grid reference. We can change the grid number here. For example, if you want to put this as the grid line 5, it's also okay. The display will change to 5 automatically. But we don't need to do that. We can keep by default as 1, 2, and 3. Okay. Before we go into this input, we turn back a little bit to span. By default, we have here is the panel width left and panel width right. Because in general, we put the member type as beam, the panel type as internal. If we change this to external, and then we go back to the span, you will see another two columns will be available because you have the extra information to put is the external edge distance left and external edge distance right. So what are these refer to? The term panel width is the transverse dimension of the slab at each column, center line, left column, and right column. For example, you have the left column here and the right column here. You can consider your panel width here, the length of the slab extension from here to here, here to here, or if not, you can consider as the beam width itself when you want to design a beam. Once you click the external panel, so you will have another extra information to input. This means that left right end of span, the external edge distance is the perpendicular overhang on the outside of the building, of the slab or of the beam, past the center line of the column at each end of the span. If you have the edge distance, or simply say the cantilever slab, you can provide extra information about the distance between the center line of the column to the external edge distance. Simply a cantilever at the edge of your building. Now you understand what is the difference between panel width left and extra edge distance left. But we are not introduce information regarding the external width. So we are going back, change from external to internal, back to the span. You see these two columns disappear now. We go on to the column. Next one is the grid. What can user define the grid here? The grid here, we have the AA here refer to the text that you can modify. You can change from value to the alphabet. For example, I change to A, B, and C. You can see that A, B, C. Now I change back to 1, 2, 3. The grid automatically adjusted based on what we provide in the input table. Not only that, you can also type AA, A1. This will also change based on the user preferences. Normally, we want to keep the grid simple and it will not confuse the user. Okay, next one, we go to the support type. In RAPT, there are 3 types of support available for user to choose. First one is 9H. Second one is fixed. Third one is a column. It depends on what kind of support that you are looking for or your framing system spanning on. So what is the 9H mean? Fixed mean or column mean? We go and see together. If you choose a 9H, meaning that there is no moment restraint at the support, the vertical restraint is always provided and horizontal restraint is provided is your column are braced at the location. It is a pin support. Second one is fixed support. Fixed support, by engineering term, it will have the full moment restraint provided at that support, as well as vertical and horizontal force restraint. Third one, you can put your support definition as a column. You can define the column above and below the beam or the structure that you design, which provide the moment restraint. If all of the column dimensions are defined as 0, it means it will go back to the 9H support or pin support. Vertical restraint always provided and horizontal restraint is provided if the column is braced at that location. For example, here, we are not going to use the pin support. We know that our beam will span to the column of the support. We change the column at the grid line 1 to the column. The information is available here. Same thing, this one change to the column. This input is available. Third, change this to the column. The information is available. This one is the column height above. For example, we have the 3.5 meter column above this. And once we click the column height, another column is available. This is the column diameter above, column width above, column length above. If we have the circular column, we can provide the diameter of this column. But we will have the rectangular column instead of circular column. We put it here. We have the column width above is 500 mm, meaning that it is the same as the beam width. This one is the length above. You see that the circular dimension of the column already disappear once you provide the input to the rectangular one. This one we put 800 as the example. Now we have the dimension of the column above and its height. Next one is the column height below. The same thing, we are going with 3.5 meter. The column diameter will appear again, referring to the input for the column below. The same thing, we have the homogeneous column cross-section. We copy and paste here, and then the information of the column is already complete, but not yet. Okay, we need to look at for some information. Now you see that at the grid line 1, the shape of the column is appear already. The same thing we do for column 2 at grid line 2, 500, 800, 3500 mm. This one I can just Control C and then Control V. The same here, Control C and Control V. Now cannot, because it has something that up here is the circular column. I delete this one. I copy this first, put it here to make the circular column disappear, and then OK. Now we see that we have the column height above, column dimension above, column height below, column dimension below. The column capital below the depressed section. For this example, we don't have the column capital. We put this as 0. Pin base below. By default, even we choose a column, there will be a pin base below the column that have the column height below the beam that we design. Next one is the percentage column stiffness. This information is very critical for the designer. Especially we need to take in care since it affects how much the moment will develop at the support, especially the negative moment at the support itself. For this information, RAPT calculate a stiffness for each column. User can then further modify this by specifying a percentage value of the calculated column stiffness. The value can be ranged from 0 to 999%. But in reality, we cannot develop a very stiff support until 999%. So what should the value is best fit to the design? Care should be taken in modifying the value, especially for punching shear calculation. Redistribution of moment away from a column is that failing in punching shear is not recommended. You see that the percentage is I22. What should be the value that we put? The recommended value is that if your beam spanning to the support connected to the strong axis of the column at ultimate limit state, a full column stiffness is recommended. However, if the beam is connected to the weak axis of the column, by contrast, it is suggested to provide only 10% of the whole column stiffness at ultimate limit state. So now, how do we know that whether the input that we provide here, the beam connected to the strong or to the weak axis? We need to inspect first. Make sure that the input value here and here will result to a correct column framing to the beam. So what should we do? You see that below here there is some tool. We have the plan view, full elevation view, and elevation view. Okay, we click the elevation view. By default, it is the elevation, and then we go to full elevation. In full elevation, we see that something is missing here at the column 3 because we have a typo error. The column height below should not be 500. It should be 3500. And then the display picture has already been refreshed. Next one, we go to the plan view. In the plan view, we see that this is the column, column, and column. What is the strong axis of the column is orientated to? We have a 0 dimension here, 100 minus 200. This one is more than 200. So this is sum together is around 500 mm. but the scale of this information is not looking correctly. So what should we do? Make sure that we inspect the scale and also the dimension provided. We go to scale or no scale. We click on this. We see that when we scale this picture, the column here are connected to the strong axis. Sorry, the beam are connected to the strong axis of the column. But if we do not scale, we see that by a bare eye, without looking at this dimension, we may think that it's connected, the beam connect to the weak axis of the column. So always be cautious when we provide the input of the column here. We can have a look on this. This is the width at this direction. It will connected to the beam at this direction. Okay, this is connected to the beam width. This is the length from here to here connected along the beam length, meaning that the dimension, if we provide a higher dimension, the column will be oriented to the strong axis. So be careful when we input this. If we provide the incorrect input here without proper inspection, we have the problem when we do the analysis and the design. Okay, since our column are connected to the strong axis, the beam are connected to the strong axis of the column, we can provide a 100% stiffness at this column. This column is about the brace frame or not. Since the RAPT, we do a 2D analysis in order to analyze and design the beam or PT system. Globally, we have to look at our global structural analysis as a whole. If our building is braced or unbraced, it will affect our 2D analysis. Normally, engineers prefer design building to be braced by a column or by a shear wall. So this engineer need to take care and decide whether you design this spanning beam to the column as a braced structure or unbraced structure. For this example, we will consider as a braced structure. Next one is the column shortening restraint. What it is here? For the column shortening restraint, RAPT gives the user the option to allow for the effect of column shortening at each column. If column shortening is to be restrained, RAPT places a vertical restraint at each selected column node in the frame analysis. Therefore, no axial shortening can occur. If the user can want to consider the column shortening at any time, have a large effect on the moment distribution, especially if higher load and column of vary length or axial stiffness are input into a run. Where a concrete frame or the loading is not symmetric, allowing column shortening is normally for the accurate solution. However, always be careful when mixing a knife edge support and column at different support location as a knife edge support. Do not allow vertical movement. So if you do the combined analysis between the different type of support, for example, you have some as a pin, some as a column, always be cautious that the pin support there is no axial or vertical movement, meaning no column shortening. But if you provide support as a column, it can be set as have column shortening or not, depend on the user define. So when we know that knife edge support should be used, knife edge support are often defined to represent a wall or transverse beam support. It is often better to model this as a column or wall but with the zero stiffness to stop them from attracting moment but still allow for the support settlement. Now we have a better understanding of what this input refers to. Next one is punching checks. For example, in this beam, there is a beam column slab system. There is no punching check required. If you are designing a flat slab, a post-tension flat slab, band beam, or transfer plate that subjected to punching, make sure that you need to check for the punching. By default, RAPT will check for the user. However, user can check and tell RAPT that no punching check is required. Once this no punching check is required, these two extra columns, such as the transverse effective depth stiffness that used to check the punching, will be disappear, as well as the transverse pressure pre-stress P over A also disappear. Okay. Now the frame information, we have complete the column input. Next one, we go to beam. This one we have the beam depth. We prefer beam depth 800 mm, and this one is the beam width at slab 500 is the beam width 500, and the effective flank width 500. This equal to 500, meaning that we model the structural analysis as the beam, and then we put the load on the beam, and then we analyze. However, user can also model the flank of the slab or part of the flank of the slab into the analysis as well. As this shape, user can also create a kind of shape similar to this information into the software and do the analysis. If user click the simple and detail, you will see that there are a lot of extra information that software we use for doing the analysis. Without doing complicated job, normally we don't often modify this one. We just simply close this from detail to simple, and then we provide a proper depth of the beam and also a proper width of the beam accordingly. Same here, once we click at this location, we will see a cross section of this one. Here we also see a cross section of this. We have the width of the beam 500 mm and the depth 800 mm. We just put a mouse around this color of the beam. We see that information has already displayed for us regarding how the beam input into the software. There is a depth top, depth bottom, top left, top width, bottom left, and bottom width. Once we click on this, the information regarding this cross section or section will be displayed. When we click on this, the information is also displayed here. For example, if I put a cut here, you will see the information below that the cut distance is around approximate 774.5 mm from grid 1, and the distance from grid 2 is around 32225.5 mm from grid 2. When I cut it here, the information will be changed and vary according to the cutted location. After this, the user can also define the drop panel. Since this example is about the beam, so there is no drop panel information need to be input here. In next example, we will go into how should we provide the drop panel so that we input and then make the RAPT to calculate for us. Same thing for transverse beam. In this example, we don't have any transverse beam. Next example, we will go together. When we provide the transverse beam, what should we look at? Layer, element, and step. Since this is a simple analysis, the information from drop panel to step, we don't need to provide. Now, we are going to the ends of how we define the general setting of the frame and also the span, column, and beam in order for RAPT software to have the information for the analysis. In the next video, we will go to see together how we should input the load, how we generate the load case, and also the load combination in RAPT. Thank you for watching this video. See you in the next tutorial. Bye bye.